So we will win it. As was introduced a while ago, I'm going to be talking about symbolic execution and some applications of symbolic execution to find something called abstract counterexamples and do equivalence checking of programs. So probably many people in this room are familiar with what symbolic execution is, but for anyone who isn't or who needs a bit of a refresher, here is a simple program. It just has some if statements that does branching on integer variables. And when we symbolically execute it, we're going to run it with symbolic variables or unknown values in place of actual integers. So we'll just say that we have some symbolic variables x and y, standing in for integers, and we're going to try to run the program. And we're almost immediately going to run into a problem here because we're asking is x greater than y or not to decide what to do with this if statement. And of course we can't tell. So we're going to branch into two different states. And in one state we'll get a path constraint that x is greater than y. And in that state we go into the then branch and just get x. And in the other state we get a path constraint that x is not greater than y. And we go into the else branch and have this if statement. And from this if statement, we again branch into two states, one for where x is equal to y, one for where x is not equal to y, and we're finished symbolic execution of this program with three possible outputs and path constraints to get to each of those outputs. If we wanted to find actual values that led to one of the points in this code, we could hand these constraints off to an SMT solver and find actual values that lead down a particular path. One of the ways people often use this is to find assertion violations. So here I have a function intersect that takes two lists and computes the intersection of those lists. And we might think that intersect should be commutative. So if I take x's intersect y's, that should be the same as y's intersect x's. And I can try to test this with symbolic execution and see, can I find a counterexample? And if I do this, symbolic execution is actually going to find a counterexample when x's is equal to 0, 1, and y's is equal to 1, 1, 0. And that's because the intersect function is defined here as preserving the ordering of elements in the first list and the number of times an element occurs in the first list. And so you actually don't get exactly commutative behavior. So in this talk, I'm going to be exploring applications of symbolic execution that kind of go beyond just this assertion checking. I'm in particular going to be talking about a symbolic execution engine named G2 that myself and some collaborators developed. G2 targets symbolic execution of non-strict functional languages, which in practice means Haskell. And this is a very high-level overview of how G2 works. We take the Haskell code, we turn it into something called GHC core. GHC is a Haskell compiler, and GHC core is one of its intermediate representations. So we get kind of a simple version of Haskell, or a simple functional language, and we do further processing to turn it into an intermediate representation specialized for the purpose of symbolic execution. We then run symbolic execution and can use constraint solving to get actual concrete inputs and outputs. There's interesting things to be said about all of this. I'm going to focus on the intermediate representation and the actual symbolic execution piece because that's the most relevant to understand the applications I'm going to be talking about. So here is a portion of the intermediate representation. So it's basically a lambda calculus with data constructors and pattern matching on those data constructors. If you've looked at work on analysis of functional programs, you might have seen something quite similar to this. We have variables, literals, lambda expressions, data constructors, application, function application, or applying a data constructor, primitive operations, let statements, and case or pattern matching statements. What's added into G2's intermediate representation is a bunch of stuff that really only makes sense in the context of symbolic execution. So we have symbolic variables, variables that we don't have a binding for, that are not bound by a lambda or case statement or let statement. We have something called a symbolic generator. So a symbolic generator, when executed, is going to introduce a fresh symbolic variable into our program. We have non-deterministic choice, choose to execute either expression 1 or expression 2. And then we have assume and assert, which take an expression to either assume is true or assert or check if it is true, and then a second expression to continue evaluation with. So this first expression is always going to be a Boolean that we're checking. The second expression is something that we're going to evaluate to continue running the functional program. States in the symbolic execution are what execution is actually done on. A state has 3 pieces in it. It's a functional program, so we have some expression that we're trying to reduce to a normal form. We have a heap, which is just a mapping of variables to bindings for those, variables to expressions. And we have a set of path constraints. So these constraints are requirements on the symbolic variables to get to a particular point in the program. So this expression is being reduced to a normal form. I'm going to leave a little vague what that normal form is for now, and we'll come back to it later in the talk. During symbolic execution, multiple rules might apply, and this is what gets us the branching behavior in symbolic execution. So we saw this with the example at the beginning. We can also see this with this example. So we have case S1 plus S2 is greater than 0 of true, run expression E1, or false, run expression E2. And this can be executed in 2 different ways by applying 2 different rules. So we could have evaluation continue with E1, and then we need, as part of our path constraint, that S1 plus S2 is greater than 0. Or we could have execution continue with E2, and then we need to say that S1 plus S2 is not greater than 0. So that's a very high-level overview of how symbolic execution works. But that is really all it's doing. It's applying a bunch of rules to states to reduce them to some kind of normal form. It's also enough of a background to understand both of these applications I'm going to be talking about. So the first application is to find something called abstract counterexamples for modular verification tools. So before we get to symbolic execution, I actually need to talk about what I mean by modular verification here. So here's a map function in a functional programming language. We have it taking another function as an argument and a list and returning a list, and it's going to apply this function to each element of the input list. And we can give this a refinement type, much like Ranjit was talking about earlier with Flux. This is a refinement type for liquid Haskell, which is kind of Flux's predecessor, I guess. So much like the refinement types for Flux, here we're going to be giving arguments names. So I'm naming the input list of A's X's. And then we're going to be giving types refinements or predicates that they must satisfy. And so here I'm saying that the output type size has to be equal to the input list size. And map does satisfy the specification. So we're going to be able to give this to our verifier, liquid Haskell, and have it say that the specification is true. If we somehow broke this, by, for example, removing the cons onto the list, so that this just always returns an empty list, we're going to get a verification error because the refinement no longer holds. And we're going to get some kind of message indicating where that error is. And here, this isn't so difficult to interpret, partially because it's a rather simple function, partially because I just intentionally made the error in front of all of you. But in practice, these can get kind of big and complicated and hard to understand. And so instead, we'd prefer to find a counterexample to show to the user. And so, as we saw with the intersect example, symbolic execution is well suited to this task. We can run the code with symbolic execution and get a counterexample. So this is what I would refer to as a concrete counterexample. So at the beginning, I promised something called abstract counterexamples. So what is that? Well, Here's another example to look at. This is a function called add2. It's doing something very interesting, which is adding 2 to a number. You can see I'm saying that in the specification. The output of add2 should be the input plus 2. And to implement add2, I've called incr twice. And the definition of incr says that the output of incr should be greater than the input of incr. So this seems true, right? Incr is adding 1 to the number, so I am getting a bigger number. It also seems to make the specification for add2 correct because I am indeed adding 2 by adding 1 twice. Unfortunately, if you give this to Liquid Haskell, or if you give kind of equivalent code to any modular verifier, you're going to get an error message. And Ranjit also mentioned this when he was talking about Flux earlier today, with an example very similar to this. The reason is that we need a better specification on incr here. And really what's happening is that when we're verifying a caller, like add2, a modular verifier is only going to use the specification of called functions. It's not actually going to look at the definitions of those functions. And so when trying to verify add2, the verifier is not actually going to see this whole picture. It's only going to see this part of the picture. It's going to know that incr's output is greater than its input, but it's not going to know by exactly how much. So how can we use symbolic execution to help here? Ideally, we'd like to find counterexamples, but there is no real counterexample here because the specifications are correct. But what we can do instead is find something that we refer to as an abstract counterexample, which indicates which specification needs to be improved and how it needs to be improved. So here's what an abstract counterexample looks like here. It says that add2 of 0 is equal to 3, violating add2's specification if incr of 0 equals 2. So the key word here is if. Of course, incr of 0 does not equal 2, but the point is that the specification of incr does not tell us enough to know that add2 of 0 does not equal 2. And if incr of 0 did equal 2, that would cause problems for add2. And so the way we have to fix this is by strengthening the specification of the function after the word if, by strengthening the specification of incr in this case, to rule out this possibility. We have to make the specification strong enough to tell the verifier that incr of 0 does not equal 2. So in this case, we can do that by saying that the specification of incr is that it returns exactly 1 more than its input, and then we'll be able to verify this code. Here's a little bit of a more complicated and more realistic example. We have a function concat. Concat takes a list of lists, and it returns a list. We're using this sum size function in the specification. I'm not showing a definition of that, mostly for space reasons. But sum size is taking a list of lists, it's taking all the internal lists, it's computing their sizes, and it's summing them together. So we're summing a bunch of sizes. And concat is just taking all the internal lists and joining them together, or appending them all together. And so the size of the output list should be equal to the sum of the sizes of all the input lists. Concat is using a helper function app or append. Append takes 2 lists and appends them together. And the specification for append says that the size of the output list should be greater than the size of both the first list and of the second list. So if we try to verify this, we're going to get a verification error. And we can use G2 to get an abstract counterexample explaining why we get a verification error. So it says concat of the list 1 in an empty list equals the list 1, 2, if appending the list 1 to an empty list gives us the list 1, 2. So of course, this is not the behavior of append, which is why the word if is there. But what we can do is say, okay, well, app is appearing after if. We have this mapping from app taking a list with 1 and an empty list to a list with 1, 2. And so we have to strengthen the specification of app to rule out this possible behavior. And so if we do that by saying that the size of the output of app is exactly the sum of the sizes of the input lists, we'll now be able to verify this code. So this is kind of a picture of what we're looking to achieve with this form of symbolic execution. We want to take code and specifications, try to verify them. Ideally, we succeed in verifying them. But if there are bugs or things that are not being verified, we can go to our symbolic execution and get either a concrete counterexample, if we can find one, and if there is a concrete counterexample, or we can get an abstract counterexample that is pointing at kind of where the spurious error is, where the specification we need to improve is. In order to find both these kinds of counterexamples, we're going to use something that we call counterfactual symbolic execution. So counterfactual symbolic execution is going to do a bit of modification to this input code. So we're going to rewrite both of these functions a little bit. Add to, we're not doing much to. We're saying that it's we're taking its definition, asserting that the specification of add to holds, and then calling the definition. Anchor we make more changes to. So anchor we've introduced a non-deterministic choice. And you can kind of think of the left-hand side of this non-deterministic choice as corresponding to concrete executions of anchor. On the left-hand side, we have the definition of anchor, and we have an assertion that the specification of anchor holds. The right-hand side of the non-deterministic choice corresponds to the abstraction being done by the modular verifier. So on the right-hand side, we have a symbolic generator, and we have an assumption that whatever variable is introduced by that symbolic generator is going to satisfy the specification, and then we just return that variable. So that variable could have any value that is allowed by the specification. So when we run this with symbolic execution, we're going to branch at non-deterministic choice the first time we call anchor. On the left, we get a concrete execution of anchor. On the right, we get kind of an abstracted version of calling anchor. And then again, in both these cases, we call anchor, and so we get a concrete execution, an abstract execution, concrete execution, and abstract execution. When we've executed anchor concretely twice, we're not going to succeed in violating the assertion because the assertion is actually true, and so if you concretely run anchor, you can't make it false. Whenever we have at least one abstracted version of anchor, we're going to be able to use that to violate the assertion. And then we throw away the states where we have more than the minimal number of abstracted functions in order to get an assertion violation, because the minimal abstraction being done most precisely indicates where we need an improved specification. To evaluate this, we wanted to see, can we actually find concrete and abstract counterexamples in code for liquid Haskell? And so we looked at a total of 7,550 functions collected from a graduate student level class at UCSD. In this class, the students were writing code using liquid Haskell, and every time they ran liquid Haskell, their code was logged. And so we had this large collection of a whole bunch of mistakes made when writing liquid Haskell code. So what we found is that in roughly 60% of cases, we could find concrete counterexamples explaining the errors. And in roughly 40% of cases, we could find abstract counterexamples explaining the errors. So in order to explain almost half of the mistakes, you need these abstract counterexamples. In total, we were able to find a counterexample almost 98% of the time, 97.7% of the time. So that's what we can do with abstract counterexamples to help debug modular verifiers using symbolic execution. Was there a question about that? This might be a good time to take a question if there was one about that. Thought I heard a beep. That might be Discord. Oh, there was no question. Okay. Yes?
Can you go back to the slide where you were showing the symbolic counterexample?
Here?
Yeah,
So actually, maybe I want to go back. Maybe I want to go back here.
Okay.
With that, so you're asking why this works as a counterexample.
Well, that seems like a concrete counterexample, right?
This is not a concrete counterexample. So this is saying if anchor 0 equals 2, we have some kind of bad behavior. And anchor 0 does not equal 2, right? Anchor 0 is equal to 1.
Okay.
So here we're kind of abstracting the definition of anchor in order to be able to violate the specification of add 2.
So it's coming up with an existential example that satisfies the specification of that function. But violates.
I think it depends a little bit on what you mean by existential example, but it's saying like if anchor 0 equaled 2, that would cause a violation of add 2 specification.
Okay.
Yeah. How am I doing on time? Okay. Okay, good. That's about what I expected. Okay. I don't have a great transition here, but moving on to our second application of symbolic execution, equivalence checking. So here we actually are going to be trying to prove something using symbolic execution rather than just finding examples. And what we're going to be trying to do is prove the equivalence of two pieces of code. So to do this, we developed a tool called Nebula. Our motivation here is really looking at some compiler optimizations that are allowed in GHC called rewrite rules. So in GHC Haskell, you can write rewrite rules in your own library. And at compile time, these rewrite rules will be applied. And the idea is you can use it to optimize code. You can say, here's a kind of inefficient or unoptimized expression. Here's a more efficient version of it. So if the user writes the slow thing, replace it with the fast thing. And so this is great if people use it correctly and are actually preserving equivalence of their code. But obviously it's bad if someone makes a mistake and they're changing the meaning of someone's code via one of these rewrite rules. Something that complicates this a little bit is that Haskell is a non-strict language. So what that means is that evaluation happens only when it's needed. It doesn't happen as soon as you're calling a function with certain arguments or as soon as you bind a variable. So to show an example of this, here I'm defining a function anchor. Anchor takes a variable x. It returns a list with x at the head, and then anchor of x plus 1 at the tail. So this is an infinite list. If I call anchor of 0, I'm going to get 0, 1, 2, 3, 4, so on and so forth forever. If I call take 20, which is going to take the first 20 elements of that list, if I call take 20 anchor 0, I get a list with the first 20 numbers from that list in it. So I get the list 0 to 19. And of course, if I was trying to execute anchor of 0 up front before getting to running take, this wouldn't happen, right? Anchor of 0 would just not terminate. And so this is what I mean by evaluation happens only when needed. We're only kind of evaluating as much of anchor as we need to in order to run the take function, and in order to ultimately print out this list. The way that this actually kind of really works is by reduction to something called weak head normal form. So this is when I promised we'd come back to talking about the normal form. Here it is. Reduction is to something called weak head normal form. Weak head normal form means you have a literal, you have a data constructor applied to things that might not themselves be in normal form, or you have a lambda expression. So these are all in weak head normal form. 9, lambda x, 3 plus 4, or just the head of 2, 3, 4. So notably, head of 2, 3, 4 is not in weak head normal form because we'd have to apply the function. But when we're wrapping a data constructor, it now is in weak head normal form. And this is what allows non-strict evaluation. So we can pretty directly adapt this for use with a symbolic execution engine. We have something called symbolic weak head normal form, and this is what the symbolic execution engine reduces things to. So anything that's in weak head normal form is also in symbolic weak head normal form, but also symbolic variables or primitive operators like addition applied to symbolic variables are in symbolic weak head normal form. When we're considering equivalence of rules, we want to take this non-strict behavior into account. And so we say expressions are equivalent if for all inputs, they either both terminate with applications of the same data constructor with equivalent sub-expressions. Again, those sub-expressions need not be reduced. They just need to be equivalent. Or to be equivalent, the expressions can not terminate or error on certain inputs. Because a compiler replacing one non-terminating expression with a different non-terminating expression is perfectly fine. So this can be a little bit subtle. Here I have a NAT data type defined. Piano arithmetic, it's either 0 or it's the successor of another NAT. And I have subtraction defined on NAT. And it seems tempting to say that if I have m minus m and 0, those are equivalent. But actually, with non-strict evaluation, they're not. Yes, it seems if these were equivalent, it also seems tempting to use induction to prove that they're equivalent, right? You have a base case with 0, you have an inductive step where you add a suck on to some variable. And you can't do that because if we have m equals sm, in other words, if you have basically an infinitely large NAT, or if you have m calling error at some point, with the first one, m minus m is not going to terminate. It's not going to be 0. And with the second one, m minus m is going to call error itself. And so in either case, this is not equivalent to 0. So what we're actually going to do to reason about equivalence is use co-induction. So co-induction is a proof technique for reasoning about infinite sequences. And to prove properties, we're going to look for cyclic patterns in those sequences. And we're going to be able to say that if some pattern is preserved by the sequence, then we have a proof that it's preserved by any number of repetitions. So I think this is probably most easily shown by example. Here I have two expressions, min a b equals a, and a is less than or equal to b. And I'm going to try to prove that these are equivalent even with non-strict evaluation. So I'm going to consider that a could just be something that immediately calls error. In that case, both of these just immediately error. A could be 0. In that case, both of these are just immediately true. Or a could be the successor of some a prime. And in that case, we get something a little bit more interesting, where we now have to think about what are possible values of b. So if b is 0 or b is error, this is pretty trivial. It ends up being true just by kind of straightforward application. If we have b equal to the successor of b prime, we get b states. The left-hand state, just by the definition of min and equals, reduces to be min a prime b prime equals a prime. And the right-hand state, by the definition of less than or equal, reduces to a prime less than or equal to b prime. And so now notice, these last two states look a lot like the states we began with, except we've replaced a with a prime and b with b prime. So we've replaced the variables with other expressions. And this lets us apply co-induction and say, well, no matter how many times we follow this reduction path, we're never going to end up with inequivalent expressions. So to evaluate this, we looked at 85 benchmarks, which were originally used on inductive theorem provers. Of these 85 benchmarks, 24 are true under non-strict semantics. So we're able to verify 22 of the 24 true theorems. We time out on the other 2 after 3 minutes. We're also able to find counterexamples for all 61 of the, I don't know why I say untrue, of the incorrect theorems, and kind of show why they don't hold under non-strict semantics. So that's Nebula. You can use it to check equivalence of functional programs under non-strict semantics. So thank you for your attention, and I'm happy to take any questions.
Okay, do we have any questions from the audience? Are there any questions on Discord? Okay, you have one in the meantime? Okay.
I was wondering how you could take these ideas and apply them to other programming languages. Do you think most of it is Haskell specific, or?
So the abstract counterexamples certainly are not. So I think the ideas there would translate very easily to any system based on refinement types, and in fact anything based on Floyd word logic also. Anything that's a modular verifier. Nebula obviously is a little bit more specific to non-strict evaluation. There's a lot of work on inductive theorem proving, right? There are languages besides Haskell that allow non-strict evaluation at certain points. So iterators in Python, for example, allow you to have infinite sequences. I believe there's iterators in Rust that allow the same thing. OCaml, you can turn on non-strictness at certain points. So, you know, Haskell is maybe somewhat unique in how much it kind of uses non-strictness as a default as opposed to a second choice. But it is applicable to other languages when you have non-strictness present.
Thank you.
Any other questions? Okay, I had a question. About the counterexample work, have you considered how to use the counterexample to kind of strengthen the types for the yeah?
Yes. So that's something that we have an algorithm for, and it's not technically under submission now, but it will be under submission soon. Yeah, we've submitted it before. Yeah.
Okay.
So it is possible to do, and it works. Basically.
Okay, it works. Okay,
Yeah.
cool. Okay. Any last questions from? Okay. In that case, let's thank the speaker again.